So by now you've figured out that I have a particular interest in following on the activities of our speaker alumni and see where their research, their work has taken them. And if in fact they move forward in interesting ways, have them back to give us a progress report. Well, the next two guys are doing fascinating stuff. Jaymie Matthews is doing it in the heavens, and Alex Tiaris is doing it inside the human body. Last year, Jaymie sent us his contribution from Kazakhstan, where he was preparing his exceptional little telescope package for boosting up into the ether. And Alex came here and played his magic algorithmic machine and showed us images of the human body and inside the human body that were provocative and startling and breathtakingly beautiful. But that aside, and before I bring them up here, I want to warn you about these two guys. They are party animals. The charm aside, the erudition aside, if they get an opening, they will drag you down, I promise. And you will enjoy it, as I have. So, Jaymie, you're first.
Thank you. This is where the party is. Thank you. You can put up the first image as soon as it's ready. Thank you, Moses. Thank you all.
Can we have image one, please?
Yeah, it's at your convenience. I'm going to buck the trend for this session. Joe and Darlene explained to you quite eloquently how we can use environments on the Earth as analogs to teach us how to explore remote places in the universe. And then Brad told us, and actually I've never met you, can I call you Brad? I feel like I know you and Sean personally already. Brad told us how if we can invest a lot of money up front as the seed, that we will get incredibly exciting results, both in terms of our ability to explore the universe around us and our ability to turn a profit while you're at it. Well, I'm going the other way around. I'm going to tell you about how we can use remote places in the universe to teach us about our home right here, and how we're doing it right now with Canadian technology that's basically bargain basement for a fraction of the cost, an order of magnitude less than these kinds of science missions would normally cost. And the reason we're doing this, we're all scientists. Everyone in this room is a scientist in the real sense of the word, maybe not with the capital S. I mean, I got into science for the money and the social life, picking up women. You're all scientists because you need to be to survive. Science is just a process. You make observations of the world around you, the universe around you, however extensive that happens to be. You look for patterns, you make predictions based on those patterns, on what the outcomes are going to be, and then you act on them. And if you're very good at making those predictions and the patterns are reliable, then you're going to get good results. And most of us here have gotten pretty good results. We're here. We managed to drive or climb into a vehicle of some sort and make it here because we've learned those patterns. Human beings are incredibly efficient at finding patterns. Better than machines. It's one of the things where we still have the edge over computers. Computers are catching up. These neural networks and genetic algorithms are starting to at least get the ability of the human recognition of patterns. But even they have to be taught by us. And maybe in someday they'll be taught by other machines that were taught by us, but we still have the lead. An example, however, is that humans can also find patterns where there aren't really any patterns. That's maybe the realm of art and mysticism. This is a part of the sky which astronomers would call Pegasus, the flying horse, Andromeda, a lovely princess, Perseus, a mighty warrior. I've picked this part of the sky because there's a star here that's very much like the sun, a twin to our sun, which we know has a planet around it, the first ever discovered around a star like the sun. And we'd like to know more about it, obviously, for the same reasons why we'd like to know whether there's life on Mars in our own backyard. Pegasus, Andromeda, Perseus, I think the pattern's pretty obvious to you, but here, let me guide your eye. Oh, going the wrong way. There we go. Oh, I love this technology. It just wants to go back and forth. There we go. Oh. Can I have a different controller?
Don't hold it down, just click it real fast.
I'm doing that.
Again.
Down? Okay. There we go. Oh. So there's the pattern. It should leap out to the eye. Actually, don't feel badly. I'm convinced that the first people to name the constellations were also the first people to ferment wine and experiment with mushrooms and possibly grow a particular type of herb. Actually, Mark Emery's in the audience, leader of the BC Marijuana Party. Can you see those things up there? Because I can't. I can see other things, however. Late last night, I recognized this pattern in this part of the sky. No, don't. I knew Moses was powerful. I didn't realize his connections extended quite that far in terms of sponsorship of this event. I'm going to show you a series of seemingly random images, which are actually part of a pattern that illustrate the story that I'm going to try to tell you in the next 16 minutes or so. Here's an image of the Empire State Building in New York City at night, totally lit up. Very famous. Here's a shopping list from Russia of an assortment of items, fairly eclectic. This is my shopping list. The wacky elephant keychain I don't have anymore. The sexy photo of Vladimir Putin you really don't want to pay 600 rubles for, I promise you. And the latest Tanya Grotter book, that's the Russian knockoff of Harry Potter, quite successful. Here is actually the almost diametric opposite to the place Darlene showed you in the Atacama Desert, where I've also visited, really one of the, possibly the driest place on Earth. There are parts of the Atacama which have not had recorded rainfall in recorded history. This is in Baja California, Guerrero Negro, where the gray whales begin their migration in the spring up northward. But it's also the home of these microbial mats, which you see here. And they represent basically the lion's share of the history of life on our planet. Life sprang into being about 3.5 billion years ago, about 1 billion years after the Earth would have formed. And for the next 3 billion years, these mats literally carpeted the Earth. And these microbes were the main life form. And in the last 500 million years, all the diversity started to come up. And now these things are the endangered species. Baja California, Guerrero Negro, is one of the few places on Earth where you can actually find them and study them. Oh, and there we go. An odd selection of films, Atlantic City, Abraxas, Guardian of the Universe, starring the famous politician Jesse Ventura, and Best Revenge with an eclectic cast of John Hurd, Levon Helm, and John Rhys-Davies, who played Gimli the dwarf in the Lord of the Ring movies and was also Indiana Jones' sidekick. Why I know that, I don't know. And here's an image of the aurora, the northern lights, which I took in another place which can reproduce Martian conditions. It was minus 60 when I took these pictures from Blatchford Lake in the Northwest Territories in March. And all of these images are connected to the story that I'm going to tell, and they're all meant to illustrate the story of the satellite that Moses alluded to. It's called MOST. Technical term, you got to have a cool acronym if you got a space mission. Stands for Microvariability and Oscillations of Stars. Also stands for Microvariabilité et Oscillations Stellaires, the perfect Canadian acronym. And it represents a bunch of firsts. It's Canada's first space telescope. It's Canada's first microsatellite, a satellite that actually does something and weighs less than 100 kilos. And Darlene told you that Canada was the third nation in history to build a satellite, and the first one to build something that actually did something, a science satellite. And I bet Michael Adams, if you did your environics polls in Canada and the United States and asked that question, I think very few people would get the correct answer. And for the first 10 years or so of the space program, Canada was a leader and a pioneer. And then in 1971, with the launch of ISIS-2, ironically on April Fool's Day, we left the space science game as a sole participant in launching our own satellites, building, designing, and launching our own satellites. and stopped doing that until this project more than 30 years later. And so we're back in the game, and I'm going to tell you how. And the good news is 45 days after this satellite went up, another all-Canadian science satellite called SciSat-1 followed it into space. So we're really roaring back in a big way. Now I'm going to tell you a little bit. The Canadian Space Agency is the main funder. I've got to include the sponsor, as Moses would understand. Our objectives are really to remotely probe the interiors of other stars to teach us more about our own star, the Sun. And also, I'm not going to talk about it much, but this satellite has the capability for the first time of seeing light directly from a planet orbiting another star. In fact, the planet orbiting one of the stars in that part of the sky that I showed you before. And so later in this year, hopefully, you'll be hearing from me again, in which we'll be announcing these historic results. Or you'll never be hearing from me again. Now, you got to put the human perspective in any mission. Here's the project in a glance. It's a suitcase in space, 54 kilos, 60 by 60 by 30 centimeters, powered, solar power. You couldn't run any of the lights in this room by our power budget. And it's possible to do this kind of science. Brad pointed out it costs $10,000 to $20,000 US per kilo to put stuff into space. So if you can do it with a lot less kilos, you're going to save a lot of money. This kind of work normally would take 500 kilos. We've done it in 50 because of innovative technology grown right here, actually in Toronto, Dynacon Inc., based in one of the suburbs of Toronto, and the University of Toronto Institute for Aerospace Studies. And I actually noticed there was a Utias proprietary figure in Darlene's thing. I don't think you were supposed to show that. And we've improved the pointing accuracy of this kind of technology by a factor of 4,000 times. That's a big leap. We're usually happy to improve things by factors of 2. We decided, let's go for the gusto, 4,000 times improvement. And it communicates with us with radios that put out less power than the cell phones that you have here, which I hope you have turned off. Here's the human perspective. MOST is also the first science satellite that weighs less than its mission scientist. I'm not going to give you any more than a lower limit on the mass. And Moses has already alluded to my activities there. And my prime contractors are Mr. and Mrs. Matthews, my parents, and I can assure you that my salary is considerably less than the $10 million that it cost to build and launch MOST, but I'm still happy to be doing what I do. The heart of MOST is an instrument, a telescope, smaller than some of the ones that I'm sure you have at home in your backyard to look up in the sky or check out your neighbors or whatever you want to use your telescopes for. It's only 15 centimeters in diameter, size of a pie plate, looks at the same kind of radiation that you're seeing with the human eye, but it measures it more precisely than any other instrument before. It's a light meter. If you've got a camera and you take a picture, there's a light sensor on your camera that tells the camera what's the ambient light level, what's the right exposure time, what's the right f-stop if you've bought a decent camera anyway. We've put that kind of sensor, a much more sophisticated version of it, at the focus of our camera, at the focus of a telescope, and pointing it at stars. And it allows us to see changes in starlight as small as 1 part in a million, 1/10,000th of a percent. Now that number probably doesn't mean very much, so let me try to put it in perspective. If you're looking at the Empire State Building at night, all the lights are on, all the windows are open, and you want to make it fainter by 1 part per million, you pull down 1 shade by 3 centimeters. Our instrument could see that. And no other instrument on Earth or in space, including the Hubble Space Telescope, has this capability. And no other instrument will until at least 2006, when the French are due to launch their satellite, which has a lot of the same goals and capabilities. Also happens to cost 160 million euro. And this is image number 1 in my story, the Empire State Building. That's how that works in. Moses said that I sent a video postcard from Russia. Now, he said Kazakhstan, and Moses is very rarely incorrect about things, but in this case, I have to take issue. He was thinking about the very famous cosmodrome in Kazakhstan, formerly Soviet territory, called Baikonur, where most of the cosmonauts go up. But we were, in fact, launched from northern Russia, 800 kilometers northeast of Moscow, a place called Plesetsk, much lower profile military base It was built in 1960. The Soviets didn't even admit that it existed until 1983. If you're of the right era or a historian or fan, if there are fans of the Cold War, you might remember that Gary Powers, the U-2 pilot who was shot down by the Soviets, created quite an international incident. That's what he was trying to photograph, was the ultra-secret Plesetsk Cosmodrome. How far we've come, where some geeky Canadian astrophysicist can actually go there with a satellite and launch it. And this is the connection. I composed this shopping list for during the month and a half that I was in Russia preparing our satellite for launch. And we were launched on this thing, which is an honest to goodness, well, honest to badness, weapon of mass destruction. This is a former Soviet nuclear missile. This thing was pointed at us at some point in an underground silo, and it's one of many that are slated for destruction by arms limitation treaties. And so we beat a nuclear sword into a scientific plowshare. It's capable of lifting almost 2 metric tons into orbit. We sent up about 170 kilos in total. That's like a family of 4 in Edmonton deciding to commission a 747 for a weekend flight to Vancouver. That's about the same. But the Russians did it for us at the bargain basement price of actually less than $10,000 per kilo, because the mission scientists can drink vodka with the best of their negotiators. Go Canada, eh? We perched our satellite at the top, our tiny little suitcase, at the top of this enormous rocket. Here's on the 3rd stage. That's a Russian technician who's putting in some of the multi-layer insulation for the thermal control. Here's the satellite with all of its protective covers removed. You can see sun sensors and the solar panels and magnetometers and all the things that make rocket science rocket science. I'd be happy to talk with you about that over the coffee break if anyone is actually interested in that. And atop this rocket, we were launched successfully into space almost a year ago. Our first birthday is coming up. And they measure launch times very precisely. And here it is. This was designed to go from an underground silo. We built our own above-ground silo. And this thing goes up like a missile. If you've watched a shuttle launch, and I think everybody has, it seems to go up pretty quickly. But the whole show lasts for a few minutes. This thing is out of sight even to high-range cameras in about 30 seconds. But a successful launch does not mean a successful mission. You first have to get into the right orbit, and then you have to make sure that your satellite survived the rough ride into space. And it wasn't for 7 hours after launch before it passed over one of our 3 ground stations in our network, one in Vancouver, one in Toronto, one in Vienna. And it passed over Canadian territory for the first time so that we could try to communicate with it. So we had 7 tense hours wondering whether we just had a useless hunk of metal and plastic up there. This is launch plus 7 hours plus 1 nanosecond. That, by the way, on the right is Glenn Campbell, not the Glenn Campbell. Well, he is the Glenn Campbell to him and to us from the Canadian Space Agency, our project manager, showing that even the government bureaucrats have a good sense of perspective. And this is launch plus about 12 hours. You don't launch a satellite every day, folks. Why did we go to all of this effort other than my arcane attempts to meet women in other countries? And you'll be happy to know that your tax dollars are not going exclusively to that purpose. They're actually going to a purpose. We're getting a big bang for the buck, a big scientific bang for the buck in this case. Thank you, folks. We're going to use this technique to see variations in stars, tiny variations in stars. It's like body language for stars. We can use the way they vibrate and pulsate, the way they spin, the way they have features on their surface that are carried around as they rotate to tell us what they're like, even though those stars remain in almost any telescope just pinpoints of light, unresolved, unlike our sun. And we're most interested in stars like the sun, but not at the age of the sun, at different stages in the life of a star, so we can put our own sun's life in perspective. In particular, we'd like to know, what was the sun like when life began on Earth? because there are a lot of mysteries associated with that. Our models of how the sun changes over its life indicate to us that the Earth should have been frozen solid at the time that liquid oceans existed and life began. So something's wrong. Either our models of the sun are wrong, or our models of the Earth's atmosphere 3 billion years ago are wrong, or a combination of them. We're also going to do all sorts of exciting stuff, but I see a yellow light there, so I'd better move because I've got 2 minutes. Well, this is where the microbial mats fit in, because that was the life form that really first dominated the Earth about 1 billion years after it was formed. And I'm going to show you an example of what we think the sun was like at the time that microbial mats ruled the Earth. It's probably not going to become a Jurassic Park movie, but... And to show this story, I'd like to use a human being as an example, as a proxy, an analog, if you will, for the life of the sun. So now, Znaimer age, now years, these are normal years, but Darlene told us about general relativity and shoe shopping. Based on my observations of Moses Znaimer, I think he fits into 1 year a lot more than I fit into 1 year, but we'll use these as human years. And I'm an observational scientist, so just based on appearance and activity level, I'm assuming he's about 40 years old. And this is where image 4 comes in. All of those 3 films featured Moses Znaimer as a supporting actor. And in fact, I happen to have on DVD Abraxas, Guardian of the Universe, along with They Came from Beyond Space and Voyage to the Prehistoric Planet, which will be available for auction, or it could be sold to Moses for 5 more minutes of time on stage. All right, I hear I got an A-OK from Mission Control. What we'd like to know is, if you were interviewing Moses and studying him in depth, you'd learn a lot about human beings, an exceptional human being, but only at that particular stage in life. And that's the situation we have for our sun. We know what it's like at its particular point, but not what it's like when it was young and when it was old. In the case of Moses, going the wrong way. I'm assuming he was a precocious child. So when he was a baby, this is my approximation. And projecting forwards based on observations, this is my scientific extrapolation of what he'll look like at the age of 95. Now we'll put this, here's the sun. In human terms, the sun is a boring middle-aged adult. Not like Moses, it's actually very sedate. It's lucky for us, it's not doing exciting things like expanding and ending life on Earth, which would be kind of good. And astronomers are able to look around in the galaxy and find other places where we see stars being born, we see baby stars, and we can see places where stars are dying. And this is our conception of what we think the sun will look like billions of years in the future when it does begin to expand and end any life that might be on the Earth at that time, on its surface at least. And so we're trying to put together the life story of the sun in the same way as you could put together a human life story. Keep in mind that the sun is middle-aged, about 45 years old in human terms. Well, one of the first scientific results from MOST, which we just announced publicly yesterday at the annual meeting of the Canadian Astronomical Society, Canadian Association of Physicists in Winnipeg, which is another analog, by the way, for Mars, if you want to... If there's anyone from Winnipeg, please, I just got that for a cheap laugh. In the winter, even the residents, though, will back you up on that one. This star is called Kappa 1 Ceti. It's about 30 light years from us, which is big in human terms, but it's basically a drop in the bucket astronomically. It's a preteen. It's an 8-year-old. If the sun is a 45-year-old, this is an 8-year-old. And like human 8-year-olds, it's hyperactive. It's spinning around much faster than the sun. It's giving off super flares of gas. You wouldn't necessarily, very interesting perspective if there were a planet orbiting around it with life like on the Earth at the same time, because this is when the microbial mats would have started to kick in our analog. And this is also where image 5 of the aurora kicks in, because it's flares like these that belch out charged particles, gas, into space, which are trapped by the Earth's magnetic field, get funneled in towards the north and south magnetic poles, and cause the beautiful displays that we call the aurora borealis and aurora australis. Well, we've been able to put a stakeout on Kappa 1 Ceti. We've been able to follow it almost without interruption for a month. and not let it escape our viewpoint from our vantage point in space. No one's ever been able to do this before for a star other than for the sun. And you could imagine for a human stakeout, if you did what astronomers on the ground had to do and give up during the daytime looking at stars, you would miss most of the interesting activity of your suspect. So we've had this continuous coverage, and we found that, like other teens, the star also has a really bad case of acne. And we've been able to use our light measurements to reconstruct what the surface of the star looks like in real time. No one's ever been, it's still a pinpoint of light. No one's seen this, but we can use the data to reconstruct it. We can't use this system, however, to show the movie, so we're going to flip over to my laptop. And I don't know, has that been done? Yes, it has. So here is our middle-aged star, the sun, spinning around sedately once every 25 days with a fairly clear complexion. And here is the preteen. That's what we think the sun might have been like 3.5 billion years ago, whipping around huge spots, huge zits on its surface. You know, that keep in mind that those large spots on the sun are about bigger than the planet Earth. So look at the size of these things on Kappa 1 Ceti. Those are the data down there. Notice every time one of these spots comes by on the visible surface of the star, the light dips down. And notice we've put on the lines of longitude and latitude on the star that you can notice that the one at the equator is gaining on the one at the higher latitude because stars are made of gas. They don't spin around like solid balls. They spin around differentially. No one's ever been able to see this kind of dynamics before. So basically, this is like a family video, like a baby picture from the past of the sun. Here's another. And this is just the first step in our attempts to map out sort of the life story of our sun so that we can try to better explain whether things like the day after tomorrow are imminent, what the sun's going to do in the immediate future, and whether we can remove the effects of the sun in our models and pin the blame, if necessary, on human activity for climate change and so on. And I've gone way, way over time, but I think Moses liked my age estimates, and so he's been very tolerant. And as have you. Thank you very much for your attention.
Well, it's one thing to slag my profession, but to get murdered on account of my acting career